confirmed interstellar object suddenly erupted in brightness at perihelion. Its light curve doubled in speed, outgassing soared, and the expected dust vanished, all in direct contradiction to every comet model. Whatever changed inside Atlas at that moment, experts could not explain. What lies beneath this cosmic anomaly? And just how far do our frameworks have to stretch to handle what's coming next? On the night of October 28, 2025, the usual hum of data from solar observatories was interrupted by a sudden spike in the numbers. Stereo A's High 1 instrument picked up an unexpected surge in brightness from 3i Atlas, with the light curve steepening to an R to the -7.5 power slope, far beyond what any comet model had forecast. Within minutes, the same anomaly appeared in SOHO's LASCO C3 and GO19's CCR1 data streams. The magnitude climbed toward 9, nearly doubling in speed compared to previous weeks. Carl Battams, monitoring the stereo feed from the Naval Research Lab, was the first to flag the jump in the team's communication channel at 0126 UTC. The numbers didn't fit. He cross-checked the photometry, then pinged the group. Comet has jumped off model. Just 20 minutes later, Chi Changjiang at the Taiwan National Space Organization replied with an independent calculation confirming the break. He pulled up SOHO C3 images and saw the same sharp rise. By 0147 UTC, both analysts had agreed something inside Atlas had changed, and the rate of brightening was now nearly twice what it had been just days before. With the comet lost to ground-based telescopes, these spaceborne assets became the only eyes on the event. Stereo A's data packet for October 28, 2140 UTC shows the initial steepening. SOHO's logs from 2210 UTC and GO19's at 0016 UTC all capture the moment the photometric alarm sounded. The timeline is precise. Battams posts the first alert, Zhang verifies and escalates, and within the hour a global network of astronomers is combing through the raw data, searching for a cause. The real-time chat channels filled with confusion and speculation. Analysts compared the new slope to every known comet, but nothing matched. The R to the -7.5 curve was steeper than Oort cloud standards, and the doubling rate was unprecedented for an object this close to the Sun. As the numbers poured in, the need for chemical follow-up became urgent. The photometric alarm had not just caught a comet brightening, it had caught the scientific community off guard, forcing them to question every assumption about interstellar visitors. For Zhang, the experience was both exhilarating and unsettling. He was known for his skepticism, rarely moved by conjecture. Yet, as he told colleagues later, the data left him with a renewed sense of wonder and a sharp reminder of how much remains unknown. Battams, meanwhile, described the moment as writing the playbook in real time. The photometric alarm was not just a scientific puzzle, it was a call to action, driving teams across continents to unravel the mystery before the trail faded into the sun's glare. Spectrographs began their work as the brightness spike unfolded, translating raw light into chemical fingerprints. The first clues came from the visible bands, strong C2 swan bands and NH2 emissions, both classic signs of volatile ices breaking free from the nucleus. These are not subtle features. The C2 bands in particular glow with a blue-green signature, unmistakable against the solar background. Kenenkich 2, a fragment of ammonia, appeared in the spectra as well, hinting at a cocktail of ices long hidden from sunlight. But the most telling evidence arrived from ultraviolet mapping. With the comet lost to ground-based telescopes, the Swift satellite's UV optical telescope became a key player. Its detectors picked up a surge of O emission, hydroxyl radicals, right as the brightness curve steepened. In comet science, O is more than a curiosity. It's a direct proxy for water, forming when solar ultraviolet light splits H2O molecules escaping the nucleus. Swift's data traced this spike with precision, showing water production rates soaring to about 5.7x 10^28 molecules per second in the 2 weeks before perihelion. That figure stands nearly 40 times higher than the output measured just a month earlier. The visible and ultraviolet spectra told the same story. Atlas was not simply reflecting sunlight, it was venting vast amounts of gas, primarily water vapor, into space. The timing of the O surge tracked perfectly with the onset of the brightness anomaly, confirming that the outburst was driven by sudden, deep-seated activity rather than a surface dust event. No dust bands appeared in the data, no broad red tail. Instead, the color of the coma shifted blue, a hallmark of gas-dominated emission. The elongated glow seen in coronagraphs matched this interpretation, lacking the classic dust features of most comets. Behind the numbers stood a team of ultraviolet mappers working through the night to cross-reference emission lines and calibrate production rates. Their task was methodical: separate the faint O signal from background noise, check for contamination from solar wind, and fit the spectra to known models. The result was clear. The gas signature surge was real, and it pointed to a nucleus rich in volatile ices, suddenly exposed and rapidly sublimating under the sun's glare. These chemical fingerprints offered a physical explanation for the photometric alarm. The comet's outgassing was not just unusual in scale, it was a chemical event, revealing a composition and internal structure unlike anything seen in local comets. As the gas continued to pour from Atlas, the mystery deepened. The next question: what kind of surface or architecture could drive such behavior? And why was the dust missing? For now, the spectra left no doubt. Atlas was rewriting the rules of interstellar comet science, molecule by molecule. Spaceborne coronagraphs became the only windows into Atlas as it approached perihelion. Stereo A, SOHO, and GO 19 recorded an object that defied the usual expectations for a comet in this phase. Instead of the familiar broad dust tail stretching away from the sun, the images revealed a large elongated coma, about 4 arc-minutes across, glowing against the solar glare. The classic fan-shaped plume of dust so prominent in solar system comets during active outbursts was absent. The brightness holding near magnitude 9 should have signaled a spectacular dust display, yet the coronagraph data told a different story. The coma's shape was smooth, almost featureless, with no sign of the sunward or anti-sunward dust structures that typically emerge when sunlight heats and lifts grains from a comet's surface. Analysts like Magillo and Zhang, working in real time, pored over the pixel-level details. They looked for evidence of dust jets, a faint tail, even a subtle broadening in the red channels that might betray hidden solids. Nothing materialized. The blue ward color shift, confirmed by filter-specific photometry from GO 19, only strengthened the case. Gas dominated, dust was scarce. This absence struck many as a puzzle. In solar system comets, a spike in water vapor and volatile gases nearly always brings a surge of dust as the escaping gas drags grains from the surface and lofts them into space. Atlas, by contrast, seemed to be venting gas directly into the void, with little or no solid material joining the outflow. The coma's elongated glow, visible only to space-based eyes, suggested an active gas-rich envelope, but failed to produce the optical hallmarks of a dust-laden event. Earth-based observers, locked out by the sun's position, followed the drama through shared data packets and live logs. Some tried to catch a glimpse with homemade coronagraphs or sodium filters, but the magnitude and geometry left them empty-handed. The professional community, too, faced a challenge. Without a dust tail to track, estimates of the nucleus's rotation, orientation, and surface structure became guesswork. The lack of dust not only set Atlas apart visually, but also complicated all attempts to model its physical behavior. For imaging analysts, the questions grew sharper. Was Atlas simply poor in dust, or did its internal structure prevent solids from escaping? Did the gas outburst strip away a thin, volatile layer, leaving heavier grains behind? Or was the nucleus built from material so different, perhaps so ancient or so processed by radiation, that it could not produce dust in the way local comets do? The coronagraphs, silent and impartial, offered only the evidence: a bright, dustless coma, a blue-ward spectral tilt, and a magnitude that defied the expectations set by every comet before it. The missing dust became the central clue, hinting at a surface and an interior shaped by a story that began far beyond our sun.